Okay, so lastly, we have causal interpretations. And again, we'll see that when you have a clear question, in this case, a causal question rather than a predictive question, you can proceed very clearly. So recall that for regression, if you're trying to estimate something like an ATE, all you have to do is use your regression model to impute or to predict what everyone's outcome would have been if they had gotten the exposure or treatment, and then do the same assuming that they hadn't, and then take the average outcomes across the whole population, assuming they all got treated, and minus the average outcome in the whole population, assuming they didn't get treated. So the issue is that this number is depends on what the regression model is, right? And since the regression model is fit from data, there's some variance in those coefficients. And so this induces variability in the ATE estimate. And of course, you have to think clearly about what are the confounders and whatnot. But more concretely, the problem is, well, what is the variance, the sampling variance of this ATE estimate, whether or not it's biased or whatnot, but how can I get at the sampling variance over here? And we already saw actually that if we have a simple linear regression model where you just have a coefficient for exposure and then some coefficients for your adjustment variables or your confounders, mathematically, your ATE is going to be the same as just this coefficient on your exposure variable. So that makes it really easy. If you want to get a standard error for your ATE, you just use the standard error for the coefficient on treatment. And of course, you should always use the robust standard error. The same translates over here. Now, the problem is that this becomes a little more complicated if you have interaction terms. And so I'll show you. This happens. So let's say, for example, that here we had a term that was A times X. So that's some interaction term times some beta hat AX. Now, A here is set deterministically to 1. So this is just going to be X times beta AX. And then over here, we're going to have a term that is A set deterministically to 0 times X times beta AX. So this one is gone, right? But we're still left with this one. And so here we're going to end up with an X times beta hat AX. And here, this one passes through, but this one we're basically going to have a beta hat AX times the sample mean of X, which I'll write like this, X bar. So what I need to know is not the variance of beta hat A. I need to know the variance of this whole thing. And now that's kind of complicated because my formula that I had for beta hat A doesn't necessarily tell me, right? If I look at just like the VCOV HC or whatnot, I can't just read off what is going on there from that matrix. It's a bit more complicated than that. So that is unfortunate. But it turns out that there are tools to do it. And in particular, there's something called the delta method, which says, okay, if you have, here we have 3 things that are all by themselves asymptotically normal. This one is, and this one is. So there's 3 random variables, and I have some function that's combining those 3 random variables. I can actually, if I know the asymptotic variance of each of those, I can derive the asymptotic variance of that function of them. You don't have to worry about that. I'm just telling you, somebody's already done that. And so we know for any kind of regression model that you can specify with any interaction terms or nonlinearities or whatever, I can actually get what is the variance of the ATE, even if it's not the variance of the coefficient. And it's implemented for you already in R. The library that I like is called marginal effects. So I'm giving you an example here where we're using this laryngoscope data, and we're interested here in the effect of randomizing for, I think this data set has like 2 different devices that they're using. And they want to know if we use this device older model versus the newer model, can we get patients intubated faster? And so they did this randomized trial where they either gave people one device or the other, and they saw how long it took them to intubate patients who were getting this particular surgery. So let's say that we are doing an analysis of this with regression, and we want to estimate the ATE. Well, here I'm specifying the regression model, and I've added these interactions between the exposure, randomization, and gender, and also interactions between randomization and age. So if I look at the coefficients here, there's going to be one for randomization, one for gender, one for age, and then the two interaction terms. So I can't just read, we already know, I can't just read the coefficient for randomization and say that's the ATE, because it's not, right? But what I can do is just predict, use this regression model, predict for both cases, setting randomization deterministically to 1 or 0, and then take the difference of those predictions, right? But then how do I get the standard error? Well, that's what this package solves. You use this average comparisons function, and this basically says I want to calculate some marginal effect based on this regression model. So you give it the regression model, and then you say the variable that I want to deterministically set to 1 or 0. In this case, it's called randomization, but here you would just type whatever the name of the exposure variable is in your data set. And then lastly, I say use the robust standard error, because this thing can also give you the classical estimate, but always use the robust standard error. So I put that there. And then boom, you get the coefficient estimate, you get the standard error. Not the coefficient. This is not the coefficient. This is the plugin, right? This is the plugin ATE. You get the standard error for the plugin ATE, not the coefficient, and all of the hypothesis tests and confidence intervals that you could want. So it basically just does all the math for you, but it is based on that, like I said, the variance covariance matrix of all the coefficients. It's just that how you have to mash those coefficients together to get at the ATE is different depending on what kind of terms you have in the regression model, and therefore the kind of formula that you get for the robust standard error of the ATE depends in a kind of complicated way on what the robust standard errors are for each of those coefficients. But the package does it all for you. All right, so let's think a little bit about this. Let's say you read a paper and it's reporting a randomized trial of cognitive behavioral therapy versus psychoanalysis. So these are two different ways to do talk therapy. And the outcome is a continuous self-reported depression score ranging from 0 to 10. And the trial reports that the AT is -2 in favor of CBT. So basically people who had CBT are 2 points less depressed than people who did not on average. And this is according to a linear model that included sex and age as adjustment variables. And it's a fairly large sample of 1,200 people. So what are the following are possible concerns? Okay. 1, unobserved confounding leading to bias in the effect. 2, model misspecification leading to bias in the confidence interval. 3, unobserved confounding leading to bias in the confidence interval. Or 4, model misspecification leading to bias in the effect. So the first one, unobserved confounding, leading to bias in the effect, this is not true. This cannot happen. Why can it not happen? Because there is no confounding. Because it's a randomized trial. Okay? So again, if you think about the DAG, here the exposure is given based on well, let's draw it as the kind of the swig. So here the exposure depends on nothing, right? It's just any kind of possible variable. It can't affect it because this is just a coin flip, right? If you want to write coin flip here, right? That's the only thing that goes in there. But obviously, all these other x's can't affect that, right? So we have this kind of a situation here, and there's just no unobserved confounding. There's no observed confounding. There's no unobserved confounding. There's no confounding of any kind, right? Some other possible, any kind of like unobserved variable that you don't have, that can't have affected the coin flip. Okay, so that's not the case. We can also rule this one out, right? Because whatever's going on with the confidence interval, if it's wrong, if it's right, who knows? Whatever it is, it's not because of unobserved confounding in this case, because there is no unobserved confounding. Okay, so next one is, let's say, model misspecification leading to bias in the effect. So the fact is, okay, we are pretending that we have, let's call this like therapy, right? The therapy kind, right, plus sex and age. We have run some linear model like this, and we're regressing like depression, right? Onto those things. we know the actual relationship between depression and therapy, sex, and age is not linear, right? Um, there's no reason that there's a linear relationship between depression and age, or any of the other kind of normality assumptions or anything like that probably don't hold. And so the question is, does the fact that this is misspecified, does that lead to bias in the effect? And like we saw, this is kind of review from last time. Like we saw last time, in general, this would lead to bias in the effect, because the thing that I'm trying to estimate is this kind of, I'll just write the conditional mean as mu. This is our estimand, our statistical estimand, or observable estimand. And we're going to, estimate it with a sample mean that's approximating the expectation. And then this regression model, right, is approximating, I'll just write the first part, is approximating this true conditional mean. And so in general, if this regression model is not a good estimate of this conditional mean, like it's a linear model when this thing is not linear, then that is not a good approximation, right? But we saw there's actually a special case. And the special case is when you have randomized exposure. When you have randomized exposure, it actually doesn't matter that this thing is a bad approximation of this, because overall, this is still going to be, these two things will still approximate each other well, which is weird, kind of interesting, very convenient, right? So in this case, because of the randomization, not only does that remove the unobserved confounding, it also removes the potential for model misspecification biasing the effect. Now we have a last one, model misspecification leading to bias in the confidence interval. Here you have to notice that this is the classical confidence interval, right? Which we saw earlier in this lecture does depend on these model assumptions. And that actually happens whether or not the exposure is randomized, because we discussed that in the context of just the mechanics of the regression model, no causal anything. So this happens whether or not it's randomized. This thing can be too small, smaller than it needs to be. It can be too big in some cases too, but generally you're worried about it being smaller than it needs to be. So this is the only one in this case that I would be worried about. Which is that since the model is misspecified, this classical CI, this classical confidence interval, is probably not what you want to be doing. Now, the solution to this is simple, right? If you just use the robust CI, then it doesn't matter that the model is misspecified, because the robust CI does not care about the model misspecification. So then that would go away as well. So if you're thinking, okay, this is complicated, it's subtle, there's a lot going on. There's many different kind of interplaying assumptions. In the special case of randomized trial, what does that do to the effect? What does that do to the confidence interval? It really is complicated. And I think it helps to think about kind of this picture here. Sorry, going all the way back. Yeah, this picture here, like where's the problem happening, right? Is it that your estimator is not a good? Well, I guess even starting here, is the thing that you're trying to estimate actually reflective of your research question? What is your research question, right? And why does it matter that you're interested in this coefficient or this ATE or whatever it is that whatever the estimate is? Have you formulated that properly to reflect your research question? Now, do you have an estimator that can actually estimate that thing in a variety of different conditions, right? So that's where the potentially confounding would come in, because if you have if the thing that reflects your research question is not identified in the data, then there is no good estimator for it. Similarly here, you might think about, is there an estimator with smaller sampling variance that I could be using? Those kinds of questions. And then here, right, how do the assumptions about the model impact what the standard error is? How can I derive that? And there could be separate assumptions to get you from here to here and from here to here. Don't have to be the same sets of assumptions. And then lastly, getting from here to here, how well can you estimate the standard error based on the data? That's typically pretty easy, and typically we just use a plugin, so it's very rare that, it's more rare that this is broken, but there's certainly research out there that says, hey, this is a better estimator of standard error than this other thing. So I think it helps to kind of think about this picture when you're trying to sort out all of the different assumptions and conditions that need to be met for your inference to be valid, and also whether the question you're asking is actually relevant to what you want to know.